Hello. So we're going to continue now with section 2.4 about conditional probability. So the fundamental idea about conditional probability is that we can have an event or an experiment where it's possible to have partial information revealed about the results of that experiment. And there is an idea that we can use that partial information to update our probabilities of events occurring for that experiment. So it sounds a little bit strange, but it's a very, very powerful idea. And it's also extremely useful for building up probability models from known conditional probabilities. So we're going to kind of introduce the idea here, cover that case of computing probabilities for hierarchical models, and then we'll conclude this section with a discussion of Bayes' theorem, which is a way of kind of inverting the probability estimates for that kind of hierarchical model. So to introduce the idea, let me imagine the following situation. So Charlie and I are going to play a game, but what's going to happen is I'm going to roll a dice, and then Charlie is going to look at it and tell me some information, but not complete information about the die roll. So first off, if I just roll the die, I can ask, what's the probability that I roll a 3? Well, we can go back to our idea of counting the number of states of outcomes that are all equally likely. The event a 3 is rolled has one outcome. There are 6 possible outcomes, so the probability is 1 out of 6. Now, Charlie is going to look at the die and tell me if the number is even or odd. So, he tells me, oh, the number that came up is even. He doesn't tell me exactly what came up, so I don't have complete information, but I have some information that the number that came up is even. So now I can ask the question, what is the probability of rolling 3 if I know that an even number came up? Well, how likely is it for me to roll a 3 if an even number came up? Well, of course, it's impossible for me to roll a 3 if an even number came up because 3 is not an even number. So in this case, initially, when I just rolled it and didn't know anything, I'd say the probability is 1 out of 6. If Charlie tells me, well, an even number came up, then the probability has to be 0. What if I rolled differently and Charlie said, well, an odd number came up? So we said this was 0 just from our intuition that it's not possible. But what is the probability of rolling a 3 if we know an odd number came up? So this can be a little bit tricky, but all that we know is that an odd number came up. We don't know which odd number. We don't have any other information. We just know that this is true. Well, now we can kind of go back and think of our the ratio of the number of outcomes in the event to the total number of outcomes. So here there's now I know that an odd number came up. So either a 1, a 3, or a 5 was rolled. And what's the probability of a 3 being rolled if either a 1, a 3, or a 5 is rolled? All of those are equally likely because I'm only told that it's odd, not any other information. So we can think about that and take the ratio of the number of outcomes in this event, which is 1, divided by the new number of total outcomes in the revised sample space, now that we know that an odd number came up, which is 3. So this is going to be 1 out of 3. So this is a example of conditional probability, where we have originally a so-called unconditional probability with no information other than the knowledge of the experiment. I'd say the probability of getting a 3 is 1. If this new information comes to light, that can change our our knowledge of what the probabilities are. So that process is known as a conditional probability. Okay, so there's a formal notation for this that we write as follows. So we write this, that P, written this way, is the probability of A conditioned on event B. So what this means is we have some original experiment, some sample space. A and B are events, so they're subsets of that sample space. And what P of A given B says is this is the probability of the event A occurring given that we are told that the event B occurred. So just like here, where if we're told, oh, an even number came up, that's an event in that sample space of 1, 2, 3, 4, 5, 6. This would be the event 2, 4, 6. And if we're told that that came up, then we had to change our estimate of the probability of 3 coming up. So this is the notation for conditional probability. So I'm going to draw this as a Venn diagram picture explaining this as follows. So if we have our original sample space, S, we can think of, well, A is some event in that sample space, and B is some other event. They may overlap, like that. So we imagine running the experiment, push the button, one of these points in the sample space lights up, and then your original unconditional probability is, what's the probability of that light coming up within the subset A. Now, what you can imagine the conditional probability as being is, imagine that we run this experiment a very large number of times, and every time the light comes up outside of B, we throw that one away. And we just consider the times that the light came up, or the sample outcome came up within the set B. Now, the conditional probability of A is among those trial outcomes where the sample came up in the set B, what's the ratio of those that where the trial outcome came within the set A? So that's the core idea of conditioning. It's like, you run the experiment unconditionally, anything can come up. If you condition on a given event happening, now you're looking at the distribution of that random event only among those samples where that random event came up within this subset, within this event B. So another way of thinking about what the conditioning process does, and this is a very helpful line of reasoning, is to say that we kind of make a new sample space. If we condition on B, we are imagining I'm going to condition on B, and now I have a new sample space that's just B. And that is my set A. So now this subset here is A intersection B. So originally I had a sample space of S, A, and B were two events inside of S. If I condition on B, I'm considering a new sample space that is just the part of S that is equal to B. And now within that new sample space, A intersection B is the part of A that lay within B. So one way of understanding what happens with conditioning is to say, this sample space has some probability of any particular event happening. Now within this sample space, we kind of renormalize the probabilities. So we are just considering events that happen within B. And now we're asking, of those events where B occurred, what was the likelihood, or what was the probability that that event occurred within this subset A? So we're looking at the probability of A intersection B relative to just the probability of B. And that's going to be what our formula for conditional probability is. So I'll just give you the exact formula. In general, we say the probability, we should write this, probability of A given B is equal to the probability of A intersection B divided by the probability of B. So the interpretation I'd like to have for this is we have our sample space here, we throw away everything in the sample space that doesn't correspond to that set B, and then we have to renormalize by B in order to have probabilities that all add up to 1. And so we kind of, another way of saying this is every time you get new information about the world, you kind of you have more of a blinder, and you throw away or discount or throw away the sample outcomes that are not consistent with the information that you just observed. And then there may still be uncertainty within the subset of things that you just observed. And that's accounted for by looking at this ratio. Okay. So if we go back to this example up here of rolling the dice, if I let my event A be the event of rolling a 3, then I can let B be the event of having an odd number. So let B be the event odd number comes up, which we can just explicitly list as the set of outcomes 1, 3, 5. So now I can say that the probability of A conditioned on B should be the probability of A intersection B over the probability of B. So the probability of A intersection B is 1, is just the probability of A, because 1, 3, 5 intersection 3 is just 3. So that's the original unconditional probability of that was 1 over 6. And then the probability of B, the probability of getting an odd number coming up is 3 over 6, because there are 3 outcomes out of a total of 6. So we have 3 over 6. So this reduces to 1 over 3. And likewise, if I wanted to ask what's the probability of having the event A conditioned on an even number coming up, how can I write, Charlie, how can I write the event an even number comes up in terms of the event B? That's right, it is just a complement, because the sample space is 1, 2, 3, 4, 5, 6, and the event an even number comes up is 2, 4, 6, so that's just a complement of 1, 3, 5. So I could write it this way. So this is A conditioned on B complement is the probability of rolling a 3 given the knowledge that an even number came up. And we know this is 0, but I just want to show exactly why. Given the formula we've just introduced. So probability of A intersection B complement. Well, A is 3, and B complement is 2, 4, 6, so A intersection B complement is the empty set. So this is the probability of the empty set divided by 1/3, which is the probability of, I'm sorry, this should be B complement. B complement, but B complement also has probability 1/3. So this is 0 over 1/3, which is 0. Okay, so the complicated, or not complicated, but more formal explanation is consistent with our intuitive understanding of what happens in this case. All right, now there's an important, simple but quite important manipulation of this formula, which is as follows. So we can write, if I just take this and multiply by P of B, I can have this. That P of A intersection B is equal to P of A given B times P of B. I'm just taking this and multiplying by P of B both sides. But now if you think about this carefully, A and B are symmetric in this formula. So I could as well have written P of B given A equals PA intersection B over P of A and do the same manipulation. So I could also say that this is equal to P of B given A times P of A. So this just looks like kind of a rearrangement of that original statement of conditional probability. But it's very often useful for building up the probability of things in a certain model. So what I mean by this is the following. So depending on what the events A and B are, P of A intersection B means A occurs and B occurs. So this is asking what's the probability of these two things occurring. What we can interpret this as saying is, well, we first, in order to have both A and B occur, first B can occur, and then we also have to have A given that we've chosen B already. And this is the same thing, just kind of flip it around. If we think of A as happening first and then B happens after A, we can say, well, first you have to have A happen, and that happens with some chance. And then if A has already happened, then you have to have B happen given that A has already happened. And then that's the chance of both A and B happening. So this will often be used with that kind of interpretation where we have two events and we imagine them happening sequentially. So one of them, imagine the process that results in one of them occurring, and then given that that has occurred, the process of the other event occurring. So this will make a little bit more sense when we discuss a specific example. Okay, so let me do a specific example. So I'm now going to introduce a very common object, which is the urn of probability. It looks suspiciously like a coffee cup, but it's the urn of probability. And so we can think of one way of generating a random process is by imagining putting different colored objects inside of the urn of probability and then drawing objects out of them. So I'm going to build up an example in this way. So I'm going to say I'm going to put 5 dice into this urn. You can see exactly what I'm doing, so there's no confusion. 1 white dice, 2 white dice, 3 white dice, and then 2 black dice into the urn. Mix it up. And now the process, let me write this on the board. The process I'm going to consider is taking dice out of the urn. And the question I'm going to ask here is, what's the probability of choosing first a black die and then a white die? Okay, so let me just so we're absolutely clear. This is an example trial of the experiment. I reach in, I don't look, I pull out 1, I pull out a white die. I reach in, I don't look, I pull out 1, I pull out a black die. Okay, So that time I pulled out a white one first and then a black die, so this event did not occur. So I want to calculate the probability of having this event. First pulling out a white die, first pulling out a black dice and then pulling out a white dice. So here's how we can figure this out using these notions of conditional probability. So the thing about this situation is, if at any point in the process I know how many dice of what configuration are in the urn, then I can very easily figure out the probability of taking one out. So let me set up the following events. So let's say let B be the event the first die is black. And then let's A be the event. The second die is white. Okay. So the key thing here is that it is not easy straight immediately to say what P of A is, because P of A is talking about what happens on the second time you pull something out, and we don't know what the composition of the die in the jar are if we don't know what the first die that was taken out is. So we'll see later how we can build this up, but immediately P of A is not easy to see what it is. However, it is easy to say what P of A given B is, because B is the event that the first die was black. If we take one black die out, then what's left in there? Well, I'm trying to stuff this out. Oh, shoot. If we take one black die out, then there are 3 white die and 1 black die in there. Oh, sorry. Which means that it's easy to write down the probability of A once we've conditioned on B. So here's how we can build this up. We're being asked what's probability of A and B. Immediately that's not clear, but we can build it up in the following way. We know that P of A is equal to, P of B, which is something about the first die. The event, the first die is black. When at the very beginning, there are 2 black die and 3 white die in there. So this event has probability 2 out of 5. So there are 2 black die and there are 5 total die. So I have a 2/5 chance of picking the black one. P of A conditioned on B, we can know, because if we've chosen the first die to be black, then that means there are then 3 white die and 1 black die. So the chance of choosing a white die is going to be then 3/4. So what we are, let me just write this down, because after drawing the first black die, there are 3 white die, 3 white dice, and 1 black die. So I'm probably beating you over the head with this point, but the thing is that we can, because of knowledge about the structure of the process, we can know what this conditional probability is. And that's going to allow us to build up the probability that we want to know. Okay, so we want to know P of A given P of A and B, so I can think of it as P of A conditioned on B times P of B, so we can just get the answer now. It's going to be the product of these two. So it's 3/4 times 2/5, so I have a 6 in 20 or a 3 in 10 chance of doing this particular configuration. of draws from the urn. So I could ask other questions about this. We're gonna return to this kind of sampling without replacement model or urn model later. So I won't dwell on it now. Okay, so we can, I just erased it, but we can continue with this idea of sequentially building up an event with more than just two events. So this I think I'll refer to as the property of higher order intersections. So I'll just note that if I have three events, A intersection B intersection C. So this is saying I have some random process, an experiment, and I'm asking what's the chance that A happened, B happened, and C happened. I can think of this occurring in a number of ways. So I can think of, well, C happened, and then B happened, given that I already had C happen, and then A happened, given that I already had B and C happen. So if I write it out that way, then I can say, well, first C had to occur with some probability. That's the unconditional probability of C. And then B happened, but conditioned on C already occurring. And then A happened, conditioned on B and C already happening. So we can factor the probability A and B and C in this way. We have a lot of freedom though, because there's nothing special about the order of A, B, and C. So I could as well write this as, I could say, well, that's probability of B conditioned on A and C times the probability of A and C, which I can write as the probability of A conditioned on, or C conditioned on A, times the probability of A, for instance. And this would just be just as valid factoring of this probability. So there are a lot of choices. Basically, any order of A, B, and C you choose. So there are, I guess, 6 in this case, different orderings of A, B, and C. And all of them will give equally valid expressions for the probability of A, B, and C occurring. So this can be really confusing if you're working with problems, because over here we wanted P of A and B, and I wrote it as P of A given B times P of B. Why did I do it that way rather than writing the probability of P of B given A times the probability of A? I could have formally done that, but the reason I didn't do that is that P of A is kind of hard to compute, and P of B given A is also kind of hard to compute. So if you think about what P of B given A, it would be saying, what would the probability of choosing the first die as black, given that you chose the second die to be white? You could compute that, and we'll learn how to compute that later, but it's not immediately given to you straightforward by the model. Whereas if you ask what's the probability of choosing the second die to be white conditioned on the first die being black, because of the structure of the problem, you can immediately write that down. Because, okay, after I've chosen the first die, I know what the composition of the urn is at that point. And so I can immediately write down what P of A given B is. So the point here is that, don't get confused by this. You have a lot of freedom for how you break this apart. There's kind of an art in thinking about, for a given random event, if you want to build up the probability of a sequence of events occurring, you have to sort of think about which can be thought of as happening first, and then the next thing happening after the first thing, and then the next thing happening after that. So for this model here, where we're literally sequentially drawing from the urn, that's very easy to say which is first, second, and third, and so on. For other things, it can be somewhat arbitrary, but it just depends on whether you can easily write. It basically depends on which of these conditional probabilities are easier to write down, and then that will guide you towards the factoring that you want to use. Okay. So I wanted to go through one of the book problems now. 2.4.22. So I'm hoping that you all have your books with you. Oops. So I'm not going to write down the entire statement of the problem. I'll read it so. I'm going to do problem 2.4.22 out of the book. So it says, a man has n keys on a key ring, one of which opens the door to his apartment. Basically, he comes home drunk and can't tell one key from the other. So he says, I'm going to choose one key, try to open the door of my apartment. If it doesn't work, I'll throw it away and choose another key randomly and try to open the door to my apartment. So the question here is, what's the probability that he opens the door with the third key? So, this has a simple answer, but it's maybe not immediately obvious at first. So what the book leads you to saying, well, clearly the probability that he opens the door on the first try is 1 over n, because he's just choosing n keys at random, one of them opens the door, and so, that's going to be 1 over n. But the probability that he opens the door on the third key, well, let's see how we can figure this out. So one way that we could do this is we could write a series of events. So let's let A be the event open on the first try. And let's let B be the event open on the second try. And C be the event open on the third try. Okay, so I guess the experiment is drunk guy stumbles home, does the thing with his keys, blah 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 blah, and then if he opens it with the first key, the event A was a success. If he opens it with the second key, the event B occurred. If he opens it with the third key, then the event C occurred. So that's the process. So what we're trying to find now is what is P of C. So here's how we can use this sort of sequential structure of conditional probability to answer the question. So maybe we can build this up first. So first of all, what is P of A? Well, he's going to always try once, and he has a 1 over n chance of opening the door on the first try. So P of A is 1 over n. Now, P of B by itself as an unconditional probability is not immediately obvious how to compute. But P of B given that A did not occur is something that we can write down. Because he only gets this, basically the only way he's going to try a second time is if he fails the first time. Now if he fails the first time, one of these keys has already been thrown away. So he's going to choose 1 out of n minus 1 keys. Sorry, that's not good writing. And we can also say that P of B complement given A complement. So this is the probability that he does not open it on the second try, given that he did not open it on the first try, is n minus 2 over n minus 1. So the reason this is that he has n minus 2 keys that don't open the door. So or another way of saying is, once we've conditioned on the first try not working, he has n minus 1 keys to choose from. N minus 2 of them do not open the door, so that's this probability. One of them does, so that's this probability. I'm going to continue this problem down here just so I don't have to erase this at this point. So now we can ask, what's the probability of C given that A does not happen and B does not happen? So at this point, the person has only n minus 2 keys, because we've conditioned on the first try not working and the second try not working, and now he has n minus 2 keys. And so this is probably is 1 over n minus 2. So what we want is we want the unconditional probability of C. What we've been able to build up is the probability of C conditioned on A not happening and B not happening, and the probability of C not happening given that A doesn't happen. So I guess that's, I didn't maybe do this in the most obvious way, but one of the factorings that I could do for this is to say that probability of C occurring, well, I guess I can first write it this way. It's to say that C only occurs if A doesn't occur and B doesn't occur. So I can write that C is, basically if you think of this, the Venn diagram, C is going to lie within A complement intersection B complement, because it's only possible to open on the third try if he doesn't open it on the first try or the second try. So I can write this, and now this I can factor using this type of higher order intersection to say this is probability of C conditioned on A complement intersection B complement times the probability of B complement conditioned on A complement times the probability of A complement. So I guess we also need the probability of A complement, but that is just following, if probability of A is 1 over n, then probability of A complement is 1 minus 1 over n, which is n minus 1. over n. So we have all the pieces now, so that we can say, well, this probability, what's the probability of getting it on the third try, given that he's failed the first 2 times? At this point, he's thrown away 2 keys. So he has n minus 2 keys, and one of them is the correct one for his door. So this is 1 over n minus 2. What's the probability of B complement conditioned on A complement? That's what's the probability that he does not open it on the second try, given that he failed on the first try. So that's saying he has n minus 1 keys. What's the probability that he will not choose the correct key? It's n minus 2 over n minus 1. And then probability of A complement is just the probability that he does not get the key correct on the first try. So this is the probability of getting the key, opening the door on the third try. And this is kind of cute, these cancel, and this works out to be 1 over n. Okay. So, most likely if you were asked this question and you were thinking about it, you wouldn't really formally write it as this factor with all these events and then factor it this way. It's really important in this class to start developing a intuition for how to set up these probabilities. So one way of thinking about this is to think about probabilities of sequential events happening. So basically every time you have a sequence of events, the probability of that sequence is going to be the probability of the first thing happening times the probability of the second thing happening conditioned on the first, times the probability of the third thing happening conditioned on the first 2. So that's another way of getting to this, is to say, we want to say, what's the probability of him opening the door on the third try? Well, in order to open the door on the third try, he needs to fail on the first try, then fail on the second try, given that he's failed on the first try, and then succeed on the third try, given that he's failed on the first 2 tries. So thinking about that process, you can say, this is the probability that he fails on the first try, n minus 1 over n, because there are n keys at that point, n minus 1 wrong choices. This is the probability that he fails on the second try. It's conditioned on him already failing on the first try, and that's why we're dividing here by n minus 1 rather than n, because the conditioning on the first try not succeeding is what puts us in the situation of him having thrown away that first key and having n minus 1 keys at that point. So there are n minus 1 keys, n minus 2 of them do not open the door. And then this is the probability that he succeeds on the third try, given that he's failed on the first 2 tries. So conditioning on the first 2 tries failing puts us in the situation of him having n minus 2 keys, one of which opens the door, and so that's the probability, that's that conditional probability. So the overall unconditional probability of him opening the door on the third try is 1 over n.